Hello everyone, and welcome to a new video format from Surface Ventures. My name is Dr. Sam McMaster. I am the event manager at Surface Ventures, and today I'm at Micro Materials headquarters in Wrexham, Wales, to bring you an equipment review of the NanoTest Vantage platform. The NanoTest Vantage is a multifunction platform able to carry out indentation, impact, and wear experiments at multiple length scales, the micro and nano scale. These can be carried out under controlled atmospheres, under liquid conditions, and at elevated temperatures. So today, we're going to explore some of the fundamentals of nanoindentation, explore the equipment in more detail, talk about applications for nanoindentation, show you how to set up an indentation on this platform, and finally, how data is analyzed. So in nanoindentation, we typically use a three-sided pyramid known as a Berkovich indenter in order to permanently deform our sample. So by permanently plastically deforming our sample, we are able to measure key mechanical properties, generally those being hardness and elastic modulus. The indenter, in this case, is typically made of diamond. Because of its high hardness and elastic modulus, it allows it to keep its shape over multiple indentation cycles. One thing to note is that you should be careful of your indentation time, that being load and unload time or loading rate, as certain materials can be sensitive to this. So, in terms of the mechanical properties, hardness is calculated by dividing the load by the projected contact area, and that allows us to calculate the resistance to plastic deformation of the sample, that being hardness. For elastic modulus, however, it is calculated using the gradient of the unload curve. Generally, when you are performing a nanoindentation experiment, you will directly measure the reduced modulus of the sample. You will need to take into account the Poisson's ratio of your material as well as that of your indenter in order to measure your full elastic modulus. In addition to these two primary properties, hardness and elastic modulus, you can also measure the elastic and plastic work during deformation, creep, and multiple other properties. So using our calculated hardness and elastic modulus, we're able to calculate key tribological ratios, those being H over E, which directly relates to the resistance to elastic deformation of your material, and H cubed over E squared, which relates to the resistance to plastic deformation of your sample. So this is key in performing tribological tests. One thing to be aware of when you're performing indentations, particularly for coated samples, is to be aware of the load that you specify or depth, depending on the mode of control that you choose for your indenter. If you choose a load that is too high or a depth too great, you will measure the substrate properties rather than that of your coating. But we will discuss this in a bit more detail later in the video. So now let's take a closer look at the equipment. We've opened the chamber door, and now we're looking at the business end of the NanoTest platform. This nanoindenter platform has some key differences from other indentation units that allow it to function as a multifunction test platform without sacrificing any of the nanoindentation capabilities. Instead of being a top-down indenter, as with so many other platforms, it uses a pendulum system, as we can see here. So on the right, we have the sample mounting and positioning system. For our bulk movements, we have an XYZ motor stage that allows us to drive two different samples mounted on a sample stub, as an example. And then for finer scale movements, here we have the nano positioning system, which uses a piezo-driven motor that can be utilized for fast and precise movements to the desired area. Generally, samples will be mounted on a stainless steel stub, such as this. This mounting system allows for various geometries of samples to be installed. You can mount quite large samples in this area. On the left, we have the indenter and pendulum assembly. So up here, we have the coil and electromagnet, which applies load, and a sub-nanometer resolution capacitive depth sensor measures the indenter displacement. This sensitive assembly allows for careful calibration of the equipment in order to perform precise measurements. This pendulum assembly that is closest here is the nano loading head. Behind that we have the micro loading head, and then further along still we have the microscope stage. This indenter is fully compliant with international standards such as ISO 14577 and ASTM E2546-07. The indenter can operate in a depth-controlled mode to reach no more than 10% into a coating if we are to perform ISO standard indentations. Alternatively, you can schedule multiple indents to assess the depth reached, after which we can then use a load-controlled indentation schedule in order to hit that same depth each time. The nano loading head can reach 500 millinewtons as a maximum load with a minimum resolution of 3 nanonewtons. Higher loads can be achieved with the micro loading head, this further along stage. This allows for a maximum load of 30 newtons. The optical microscope can be used to locate specific areas on the sample to indent with a repositioning accuracy of less than 0.5 microns. As mentioned before, this platform is extremely versatile and able to cater for multiple industries and different testing regimes. With an environmental chamber, controlled humidity, and reduced or oxygen or purged environment can be selected when choosing your options. One thing to note is that if you are choosing this, you would have to choose this chamber when you are purchasing your indenter, as it would surround all of the assembly that you see here. As an additional option, high temperature testing can be conducted. On this particular platform, temperatures up to 850 degrees Celsius can be reached for nano indentation, nano scratch, and nano impact experiments, or their corresponding micro load variants. Low temperatures of -20 can also be maintained. For a larger range of temperatures, a different version of the NanoTest platform should be used. This is known as the NanoTest Extreme. And instead of this more open environment, it is based in a vacuum chamber, allowing you to reach up to 1000 degrees Celsius on the high end and temperatures as low as -40 degrees Celsius. The liquid cell, which will be mounted on the sample stage, allows the sample and probe to be immersed in liquids. This can be augmented with electrochemical measurements. The modularity of the platform allows you to configure the system to your needs. So you can choose a combination of these modules to suit whatever it is that you need to do. The base function of the system is regularly updated. However, for example, the newest update is the Platform 5, which includes rapid indentation mapping, fine scale mapping, fast indentation, increased scratch capabilities, and a soft contact capability for low stiffness samples. In the software, scheduling is included, so you can queue up tests and set up a test to start later in the day, as an example, so that you can minimize vibrations around the platform. I myself used this platform during my PhD studies to characterize DLC coatings with nanomechanics in order to inform on their tribological performance. The nanomechanical mapping capability can be used to characterize alloy phases for high entropy alloys or duplex steels, as an example. The micro and nano impact modules, one for each loading head, can be used to predict performance under erosive conditions and can also mimic the repetitive contact in end milling. Micro Materials have recently improved the impact module, something that we will cover in a future video. The high temperature feature I mentioned earlier is favored in the aerospace industry to study the properties of coatings in extreme environments. But, as mentioned before, we're going to focus on the nano indentation function of this platform, which we will explore further now. So, to do this, we click on Experiment, Indentation, and for now, we're going to import a schedule. So this is something we have predefined, but you will still see all of the same variables that you can use to define your indentation. You can make some edits to your initial indentation position, and now we have the indentation schedule preview window. So this allows you to set experiment type. For now, we're just looking at a standard depth versus load hysteresis. Our thermal drift correction is set to collect post-indentation data. In terms of method, we're using load control. We're using multiple loads here with a minimum load of 5 millinewtons, and then finally a maximum load of 500 millinewtons. You can manually set the spacing of loads, but for now we've left that as automatic. In terms of load ramp control, we're using fixed time load and unload. Okay, so that is a loading time of 5 seconds and an unloading time of 5 seconds with a dwell period at maximum load of 5 seconds. In terms of your indentation grid itself, you can choose a number of columns and rows. For now, we simply have 10 indentations programmed and a retraction distance in each indentation of 15 microns. Okay, we select that, click OK. In terms of contact method, we are just proceeding with standard as opposed to using the soft contact. We are going to select used fast contact procedure. This hugely speeds up the indentation. And now we're going to begin to run our schedule. Okay everyone, our indentation schedule is now complete, so we're going to focus on the computer monitor and proceed to analyze the data that we've just collected. Okay, so now let's just take a look at the software for our data analysis. So our indentation is complete, and we can look at analysis, indentation, and review data file. So what I've done with this is I have already opened this just to check the calibration terms. But we have an original file here, that is this one. We're going to load this in. So what we can see here on the left is our load depth curve. Okay, and then on the right we have our analysis parameters. What you'll notice, because we have not specifically analyzed the data from this indenter, it says data not analyzed, and we do not yet have hardness, reduced modulus, and all of the other parameters. What you will notice with this is that you can scroll through. If you remember, we selected indentations at multiple loads. So as we scroll through this, you will notice that the load increases. Let's click on all now. We can now look at each of the indentations. You can see very nicely that the loading portions of this overlay, and then we will calculate from each of these the hardness at our maximum depth, and then the reduced modulus at the unload curve. In terms of data export from this, you have multiple options. So you can export the actual graph window itself to clipboard, the experiment report, dwell data, and all of the analyzed data once we've done that. Okay, so for now, I'm just going to show you how you would analyze this. So let's exit. Now we're going to go to indentation once again. And because we're using a pyramidal Berkovich indenter, we're going to select this, perform analysis, add our file to the list. This is our original one without the analysis already applied. We're going to click select. Okay, we're going to have power law fit. All of these parameters are okay. You can, of course, select these if you want energy calculation, strain rate, loading rate, and so on. When we set up our indenter, we did a thermal drift correction after the indentation, so we're going to specifically select post-indentation data if possible. Now for our diamond area function, we're going to use a general function, a beta factor specific to the Berkovich indenter, so that is 1.034, And then for our general function, we're going to select a manual polynomial. Okay, A is going to be 0. B, we're going to set that to 1200. And then C as 24.5. Okay, so this B parameter is effectively the sharpness of the indenter. So this will change throughout the indenter life. And then 24.5 is specific to the angle of the indenter. So if you were to use a different type of indenter and doing any kind of area function, you would notice this polynomial and this term specifically would be different. Okay, so now that we're happy with this, what we're going to do is click Analyze. Start fitting at 40% of data. That is absolutely fine. So we're going to click Continue. And now at this point, the NanoTest software is going to run through each of our indentations and analyze those. That's now complete. So we're going to quit out of our analysis, pyramidal analysis, and then go to Review Data File. Okay, so now we're going to go to our original file. And what we'll notice now is that our analysis results are present. So we can see at this low load, we have a slightly higher hardness. We are sampling a smaller depth into the sample. So case hardened steel, our shallow depths are quite hard. As we progress along the indentations, as the load becomes higher and the depth increases, the hardness decreases. What you'll notice is the reduced modulus changes with much less, it changes much less. Okay, and then we can click All once again. What you'll see is the software will then compile an average. So our average hardness across all of these loads is 9.997 or 9.98 to that number of decimal places. Reduced modulus of approximately 220. So that is all that. And now, if we are to go to export, we can then export these analysis results. You can export effectively all of the hysteresis data if you want to plot each of these in whatever software of your choice, Excel or Origin, anything that you can do plotting in. And that gives you flexibility to handle the data how you want to. But in terms of the analysis, the NanoTest software covers everything. And that is it with the analysis. Okay, so as you've seen, nanoindentation is an extremely powerful technique for characterizing coatings and bulk samples. The NanoTest is able to perform scratch, impact, and wear experiments in addition to indentation. Those modules we will explore in future videos, but for now, we'll leave you with links to technical notes from Micro Materials for you to explore at your leisure. Thank you all for watching. We hope you enjoyed this new video format from Surface Ventures. Thanks to Micro Materials for having us here today to do this recording. We hope this was a useful equipment review of the NanoTest Vantage, and we wish you all the best with your own indentation experiments.